Last summer, we were involved in a really special project. Niantic and Playcraft organized a jam to test the Niantic AR framework called Lightship. Our job was to create something using the Lightship API and provide them with feedback. One of the main features we developed for our application was a procedural ivy that covers the world around you. Today we are going to show you how we created this on Unity. During the last week of July, we had the amazing opportunity to take part in the Lightship Global Jam. This experience was crazy. For a week, we designed and worked on an experimental app that uses the feature displayed by Lightship. We also had the possibility to connect with the Niantic team and ask all the questions we had about the framework. In short, the app we have created is able to spawn a procedural ivy along the surfaces detected by the Lightship framework. Once a surface is detected, we were able to do a raycast on it, detect the collision point and start the generation of the ivy. The first thing to do is to find the points that make up the branches of the ivy. For each branch, we use a recursive method to compose a list of points. For a more compact syntax, we extended the list with a joining method able to match two groups of data. The algorithm to find the points is quite easy. Basically, you have a bunch of possible cases and you go through them. You go on until a collision happens or if you run out of possibilities. For each step, it is important to know the direction, the normal, and of course the position. To find the point 1, we need to cast a ray toward the normal vector. If a collision occurs, P1 is the collision point. Otherwise, P1 is the point plus the normal vector multiplied by the segment length. From here, we cast another ray toward the direction vector. As we did before, if a collision happens, P2 is the collision point, otherwise P2 is P1 plus the direction vector multiplied by the segment length. We continue in this way, changing the normal and the direction vector consistently until P5. This path allows us to cover all cases. When we find a valid point on this path, we use the joining method to return it and recall the recursive method. For some points, we also do an additional check to verify if there is something in between. If it is the case, we add 2 more points in the middle. After the creation of the list, we proceeded to build the mesh around the nodes of the ivy. For each node, we created a circle and found some points on it. Every point represents a vertex of the mesh we want to build. To create the mesh, we also need to set up the triangles, referencing what points are part of which triangle. The order is important. Keep in mind that Unity uses a clockwise winding order for determining front-facing polygons. The normals are simply calculated from the center of the circle towards the current vertex. Unfortunately, this is not enough. We need to know how to orientate the circles we built around our nodes. To be sure to not deal with some unreliable rotations, we need an easy and practical way to do that. Therefore, we created a data structure called Ivy node where we could save the position and the normal vector of every node during its creation. With this data, we were able to use the method lookRotation with the direction and the normal of each node. The direction is the vector between one node and its successor. With the mesh in place, we created a shader to drive the growing effect. The first thing was to move the texture along the y-axis over time. Because of that, we needed to create the UVs of our mesh. The UVY value of each vertex was calculated by remapping the node index between 0 and 1. After that, we clipped the mesh using the same amount we used for the offset. In the end, we were able to move all the vertices towards their normal to narrow the tip. Animating this value over time leads to creating a convincing effect. To decorate the ivy, we also wanted some leaves and flowers to cover it. Fortunately, every node has a normal which we can use to orientate and calculate the position of the prefabs. Using a random value, we populated every branch in a different ways to achieve a more realistic look. Both flowers and leaves use a shader that handles what the appearance is with a similar logic to the ivy. We also proposed some textures to use as a color mask. Using a lerp method, we remapped the colors based on the green and the red channel. At this point, the look of the Ivy was complete, but the performance wasn't very good. Of course, this depends on how many branches have been spawned. Therefore, we created a system to combine the meshes that share the same kind of material. Every time we have a new mesh, we ask our manager to insert it in a mesh group. This is a data structure we created to group all the meshes according to the properties of their material. When ready, we can call the combine all method of the manager. This method asks all the mesh groups to combine their meshes. To do so, we created a combine instance and used the combine meshes method. Eventually, we destroy all the game objects and download the unused assets. Looking at the statistic of our scene now, we can appreciate the performance improvement. This is the final result. The code is available on GitHub. If you want to support us, you can also buy it in the asset store. This is completely symbolic since the code will remain open. Let us know in the comments below what you think about this project. Don't forget to subscribe, smash the like button and follow us on the other socials. See you next time. Cheers.